So I created a snake game. Yes, this flickery piece of garbage. I know it sucks. But hey, it works. By the way, I also created the operating system this works on. I'll explain the reason why this is flickering later. There's actually some lore to it. Now if I press escape, I'll go back into the shell of DimOS. Yes, that's the name that I chose. I'm sorry. So this command shell is the interface provided by the operating system. Like in say Linux, you have a GUI and a shell as well. But in this case where we don't have GUI, a shell is all we need. And this excuse of a shell has a few commands that you can view by help. So what we can do is ls the current directory, create a directory, create a file, write to it using fprint, or read from it using cat. Or we can just run the snake game again and play it with the flickering screen. That's it. That's all the OS offers for now. But obviously, there is a lot more groundwork done in the operating system to run them, like memory manager, process virtualization, virtual file system, interrupt handling, and so on. Alright, so now let's talk about how I made this operating system and how it's done in general. So first of all, this is the GitHub repository for DimOS. So here are all the things that I've covered. A basic demo picture and all the build instructions. You have to install an emulator to emulate a hardware, a cross compiler to build it, Zora ISO for ISO, and then you can just clone it with submodules, make limine or limine, I don't know what it's called, but I'm gonna call it limine because I'm used to that, and then use all.sh to clean, build, and run, or separately call the scripts. So let me show you a demo. So I can just call all.sh because all the requirements are already installed. Then QEMU starts up, I select DimOS, it loads up, I can do a help, I can start snake game, it flickers because there's lore to it, press escape, ls cd proc, ls. That was the program. Now let's address the elephant in the room. How do you begin making an operating system? So before you make an operating system, you have to understand one thing, what that is. So let's say this is your hardware. So let's say this is your hardware, and this is you. So I'm gonna remove the brain because we are stupid. And then you want to interact with the hardware. Why? Because your movie is stored in the hard disk, right? If you want to run a calculator, you need the RAM and all that. So that's why you want to interact with the hardware. And how you can interact with the hardware is you have a layer of abstraction called operating system. Now this interacts with the hardware and hardware interacts with this. And now all your programs, and all your programs like Chrome, this kneeboard, or any other program, they interact with the hardware. No, they interact with the operating system. And so this is the job of operating system. It is to interact with hardware and provide an interface to applications. So that's what you want to do. Now, so here's the first challenge, right? When you're writing, let's say, a terminal application, you use headers like IOStream to output to console, right? But this IOStream is a functionality provided by the operating system. So you cannot even print because you have to interact with the monitor. But how do you know how to interact with the monitor? You need an operating system for that. But if you are the operating system, you have to figure that out on your own. So you cannot use IOStream. Similarly, if you want to use new delete or malloc free, you cannot use that because this is also provided by the operating system. But you being the operating system, you have to provide it yourself. This means you cannot use vector either. And in fact, in general, you cannot use standard libraries. So this is the environment that we're dealing with. It is called F freestanding with no standard libs and a bunch of other flags. So we do not have the standard libraries, and now we still have a few headers like standard def, which has definition of size t, or standard int, which has definition of sized integers like uint 32t. So all these things. So you have very basic headers, and then you have to use a cross compiler to target a specific architecture. So in my case, I use this one, x86-64. So x86 is the ISA 64-bit, ELF is the executable type, executable loader of something something, and GCC is the compiler. And using them, you compile your program. So this is your source code. You compile that into a binary program, which is your ELF file. But here's the question, how you're going to run this file? Because if you want to run a normal application, you use a command shell, but you don't have a command shell. You have to run this at boot process. And that is what happens. So what you do is you need an application called bootloader. You must have heard of Grub, or what I use is Limine. So Grub loads you into 32-bit, Limine loads you into 64, so I use Limine. I actually used Grub before, but then I moved to Limine. So what happens is you bundle Limine with your kernel, so kernel.binary, so which was a binary file, to create an ISO using XOR ISO. And then at boot time, what happens is there's a thing called BIOS, basic input output software, and it loads, so it checks all the hard drives and then it loads whichever hard drive has a boot sector. It's not completely correct, but remember, I'm gonna boil down a lot of explanations to make it fit in a video. Now it then loads the bootloader, and then the bootloader, so you have the Limine bootloader, it does some stuff like it goes into 64-bit. So initially the system was in 16-bit, you go to 32-bit and then 64, and then it starts executing your kernel. And that's how you can start running your C, C++, or any code that can compile to plain binary without operating system dependencies. So that's what happens in the bootloading process. If you're interested more in the bootloading process, I would highly recommend you to read this book, Writing a Simple Operating System from Scratch by Nick Blundell. Now this does not have much about operating system itself because it's a partial book. It's not completed, but it does cover bootloader and shows you how to write your own bootloader. I made a video related to bootloader that is right here on the screen, somewhere around here. That was inspired or basically code copied from this book only. Before going ahead, I would like to mention that in operating system dev, you need a lot of theory, right? So you're gonna have to study a lot of things. So if you want to do operating system dev, let me show you a bunch of resources from where you can start. So this is for bootloader. Then this operating system dev wiki is a great resource overall. It does exaggerate on the difficulty of operating system dev, like it says you require beginner mistakes. Yes, so it says like you require a decade of experience. You don't. Half a decade is enough, but yes, it is a complex topic, right? So these are the things, and if you are interested in getting started with Limine bootloader, there is a bare bones tutorial with Limine. This is great. This is actually a very good starting point. Also, I would still recommend you to read through the normal bare bones, which use Grub and 32-bit, because there's still a lot of information to be had. Also, there is a meaty skeleton, which is basically a proper well-built structure for operating system, but it's kind of sucks. I used it. I had to refactor a lot of it, so you can use it. You may not want to use it. I would recommend just go with the Limine one. So yeah, these are like some beginning tutorials. You can read them. Then there is a holy bible of operating system dev, that is the architecture manual. So since we are developing, or I was developing x86, Intel 64 IA32 architecture manual was great for some things. I obviously didn't read a lot, but these are great. It is the source of truth essentially, but it does require some grit to be able to read it. Now, you also need to know a lot of operating system theory, like what operating system conceptually is required for, right? For that, I would highly recommend this book called Operating System 3 Pieces. It's a great book. It covers topics and some implementation details as well. So it's great. There's also a draft for XV6. So XV6 is a tutorial operating system made for teaching. So this is essentially its documentation with a lot of implementation details. So you might want to give a read as well. I also read this. It was great. Then there are some old tutorials which I would not recommend you to follow step by step, but would be very useful to read. So this Broken Thorn, it does cover a lot of things. There's also James Molloy. However, James Molloy has a lot of known bugs. So if you search this, you'll find a lot of bugs, and this might help you if you're following that. But again, in OS Dev, all these tutorials are actually pretty old and you should not follow them step by step, but reading them can be really helpful. Similarly, there's this little OS book which covers booting again in detail, and then the further you go, the more high level it gets. But it is a good book to read once or twice or thrice to get a overall high level overview of what OS looks like. Also, when developing, you are gonna need to know what ABI is. That is again a very important topic. So here, if I search ABI, so System 5 ABI, I would highly recommend you to give it a read. Just like this is just one page, but it will save you a lot of debugging. And if you are interested in more in-depth ABI, you can read Itanium C++ ABI. It is actually, I think, used in most common compilers and architectures. There's also a very great Reddit post where this guy created a operating system and ran a Game Boy emulator in it. But more importantly, he wrote down a pretty long list of things you can do while writing an operating system. I would highly recommend you to read this multiple times as well. Then there is also a very good operating system dev server called osdev.gg. I mean discord.gg osdev. Alright, so let's see. I've talked about all the resources that you can go through, and I went through personally. And let's see the features. So Limine bootloader I've explained. Now 64-bit, so I would like to give you a brief introduction of what bits are. So 16-bit means register size is 16-bit. 32-bit means register size is 32-bit. 64-bit means register size is 64-bit. There's actually a lot more, like there are a lot more differences, like the way you set up GDT, global descriptor table, the way you set up paging, and all that. Actually, these are, I think, the two main more differences, but in general, this is the most important difference, I would say. People can disagree. I disagree myself as well. And so that's a basic idea of what bit modes are. And if you are interested, so here's what a 64-bit accumulator register looks like. And then the first half of it, or the lower half of it, is EAX 32-bit. The lower half of that is AX 16-bit. The lower half of that is 8-bit AL accumulator lower, and upper half is accumulator high. That's how like registers work, because with generations wider registers came, but they actually came with space efficiency. And what registers do is, let me show you. So if you have a CPU, okay, that rhymed weirdly, and you have RAM, so the way you interact with RAM is using a CPU bus. And now the way you do that is you put or get memory from registers, and then you call CPU bus. I might not be 100% correct, but this visualization is enough. So this register memory is very fast, in order of few CPU cycles only, whereas reading from RAM is very slow. So yeah, that was a brief introduction of this, and now let me show you what happens when you start the program. So because you are running in a freestanding environment, you actually do not have int main as a starting point. It is up to you what it should be. Okay, what is this? Let me just discard the changes. Okay, so the starting point is defined in my linker script. So in linker.ld, as you can see, I've defined the starting point to be start, and then in my boot.s, which is assembly dialect for GNU ASM called GASM. So I'm using that, and this is the entry point. First of all, what we do is we set up descriptor tables. So I'm not going to explain what GDT is, but I'm going to explain what IDT is, because that's what also it sets up. So IDT is called interrupt descriptor table, and here's the requirement for it. So this is your operating system. How does it know when a keyboard is pressed? So one thing it can do is it can ask the keyboard every time if a key is pressed. Let's say every 10 milliseconds. You can already tell this sucks. So, and this is called polling. So the way this happens is we ask the hardware to tell us whenever a keyboard event happens, and that happens through an interrupt. So whatever operating system is doing, it will stop and process the interrupt. This is called interrupt service routine, ISR, handling, whatever. So there's a lot of interrupts. There's hardware interrupts like keyboard, timer interrupts to interrupt your operating system periodically. There's also errors like maybe page fault or something like that. So for that, you need to set up the interrupt descriptor table to specify which handlers you have to write. Then what I do in kernel early, let me show you, is I call the global constructors. So because I'm using C++ and C++ has this concept of constructors and destructors, when you have global objects like this, before the program starts, C++ calls the global constructors. But here it won't, because that setup is not in our current compilation model, where we don't have standard libraries, we do not link to standard libraries and all that. So we have to call them manually, and this code snippet I got from the OSDev server itself. So what I'm doing is I'm just going through the init array, initialization array start, initialization array end, and calling the constructor, and where this is defined is linker script. So yeah, as you can see, I'm providing the constructors. So yeah, this is what I do. So once my kernel starts, it first of all does some setup, and now it's time to call the kernel main. Let me just change this. Oops, I cannot paste this like this. Okay, so kernel main. So here's the actual entry point. Now I wanna write an operating system. So operating system's most important duty is to provide an API to interact with the hardware, right? So it needs to know how to interact with the hardware. So here are a few very important hardware that we cannot ignore. The first is RAM. We have to provide an interface so that we can use the RAM properly. So that requires writing a physical memory manager. Now this physical memory manager will deal with physical memory. Then it is managed by a virtual memory manager, which deals with a virtual memory. So if you do not know, there's this thing called paging. Now the way paging works in a nutshell is that you have virtual memory space from 0 to whatever, right? And now you have divided it into chunks, usually 4 kilobytes. And now every chunk of this virtual memory can point to some chunk of the physical memory. So this is the actual RAM. So this way you can point somewhere else. This one can point here. So this is very useful to have a clean address space, so that every process has all the memory starting from 0 to whatever your limit is. There's some other reasons as well, like there's not much external fragmentation, but again, this is a lot of theory. I would recommend you to read books, or I can explain in a proper dedicated video. So This is what paging is, and that is managed by the virtual memory manager. And this is at least the structure I have. And then I also have a heap that will help me, that uses VMM, right? And now this will help me to call malloc and free, and hence new and delete as well. So this is what I do. First of all, I get the layout of the memory in kernel, I mean in the RAM. So this layout is provided to me by the bootloader. So as you can see, there's some bootloader reclaimable memory, there's some usable, there's some reserved. So I deal with all that, and then I provide that layout to my physical memory manager, which is here. So I initialize that, and then I initialize my virtual memory manager and initialize my heap. Note that this is all in the kernel space, right? There's actually two spaces, or whatever you want to call that, a kernel space and a user space. So this is a kernel space. So this has all the privileges, so it can interact with hardware essentially. All right, so it is ring 0. And then there is user space where actual applications run, and this is ring 3. It does not have the ability to interact with hardware. Instead, it calls the operating system to do the interaction. For example, if it wants to read a file from a hard drive, it will call read system call, and read system call will like trap into the operating system or interrupt into the operating system, and then operating system will interact with the hard drive, and then it will return the data. So that's what user space and kernel space is. My operating system is only in kernel space for now. Now there is a reason, I'm going to talk about it in the end, why I have not written user space yet. So yeah, because everything is in kernel space, I have just like these static objects. I initialize them, and yeah, so here's my memory management setup. So let's talk about the second big thing, that is process virtualization, so or kernel threads. So because I'm in kernel space only, I am not calling my processes or threads process, but I'm calling them threads or kernel threads. So here's what kernel threads are in my operating system. So what I can do is I can create a thread, and I have to add it to a vector. And what a thread is, I define it by a few things. The stack size for the thread, because the thread's execution is different, right? So the stack size for that thread, some initial register values, so registers, and also a function to call. And now what happens is, every some milliseconds, I have a device called pit. This will interrupt my operating system every few milliseconds or whatever I define, and then operating system will handle that interrupt. And the way it handles that is, it goes and looks at the thread list, the kernel thread list, and if there are multiple threads, it will switch to some other thread. Right now I'm following round robin, so it will switch to the next thread. So it will switch from here to here, and then this thread will start executing. Then after a few more milliseconds, this will stop, this will execute, then this, then this, then this, then again this. So there is resumability for execution of these threads. Now you might be wondering, how does that work, right? Personally, I have also wondered, how does that even work, right, in a very generic way. So the way that works is, let's say your thread is running. It has a stack space, right, where all the call stack information and stack variables are. And then you have your program counter, which is executing through the binary information for the function. And then you also have some register values. So when you have to switch from this thread to another thread, right, so this is another thread, the way you do that is you save all the values. So the program counter, PC register, all the other registers like RAX, RBX, R1, R2, all these into the stack of this kernel thread itself. And then you jump to some other kernel thread, right? And now remember, we have context switch from this thread previously, right? That's why we are coming back here. So what that means is on the stack, all the values are at the top, like RAX, program counter, RBX, all those things. So you just pop them and then start executing. So that's how you save the state. Now, if we were in user land, we will also need to switch the virtual address space, because every process has a different virtual address space, but because all these threads are in the kernel itself, they share the same address space but a different stack. So that's how virtualization works, and it is actually one of the most trickiest, I would not say trickiest, but hardest to debug code. Oh no, not even that, but I would say it is one of the most fun code. Let me show you how it works. So let me go to interrupt. So not interrupt, let me go. I just closed the VS Code. Okay, great. Good job, me. Good job. So yes, here I want to open the K thread. So yeah, let's have a look at this. So as you can see by this macro, I push all the registers and I pop all the registers. Come on, get out. My laptop is getting slow. So here's how it happens, right? Actually this and this is connected somewhat. So when an interrupt happens, first of all we save all the state, all the registers, then we call the interrupt handler. Then when interrupt handler is called and it decides which kernel thread to go to, it will call return from interrupt, and it would store the interrupt frame, as you can see, all these things, and then jump to return from interrupt. And as you can see, now this return from interrupt is happening for different thread. Don't worry if you're not following this explanation, it's a bit convoluted as well, it's a bit stupid as well. And once it returns from the interrupt, it will pop the registers and start executing for this new thread. So that's the structure of how process context switching happens, or I call that kernel thread. So yeah, there's preemptive multitasking with a round robin scheduler. Now this is concurrency. Although this is a single core, there is concurrency. So we need concurrency primitives like mutex, condition variable, and semaphores. So again, this book, I read from this and implemented it. So let me show you my primitives. So I have a mutex lock, I have a condition variable, and I have a semaphore. So these two things are the actual main things. Semaphore is just a wrapper around these two things. So let's go to the implementations. So the way this works is this. Again, this will take a lot of time to explain because this is too technical. But the idea is that whenever a thread calls the mutex.wait, right, or mutex it tries to acquire a mutex, it checks if the mutex is available, right? So if it is not available, it is pushed into a queue where it waits for it to be available. Once the owner of mutex releases it, the person, or I mean the third thread which is waiting for it, comes out of the queue and acquires it. So that's why you must be seeing that I have a queue, a flag which is the value of mutex, and also a lock, because if you see this function also needs to be concurrency safe, and that's why we have to do a spin lock. Spin lock essentially means that whenever we are waiting for mutex, we do not suspend our thread. In this case, notice that it is pushed into queue and then the thread is suspended, and it won't be reactivated unless the a mutex is given to it. So scheduler does not pick it up. Whereas in spin lock, we do not sleep our thread, we just do a while loop. So while not get. So yeah, that is concurrency. Condition variable is also very similar. Again, not going into very deep details, but it is also very similar. And then condition variable can notify as well, and so all the important things. And then there's semaphore. Semaphore just has a mutex variable and condition, mutex lock and a condition variable. So that's my concurrency primitive. Now let's talk about another very big feature, the virtual file system. Now again, for virtual file system as well, I recommend you to read operating system theory. And my implementation of virtual file system tries to be similar to Linux in API at least, but again, it sucks. So here's what virtual file system is, in my case at least. So I have a file system tree, right? And now every node in this file system tree belongs to a separate, belong to a separate file system. And that file system is a concrete implementation of a file system. For example, so this is the virtual file system, right? This covers all the file systems. Now in /dev/1 could be my hard drive 1. In /dev/2 could be my hard drive 2. So yeah, I can mount different file systems, and they can have like a different file system type, right? NTFS, FAT32. None of these are implemented, but hypothetically, I have only implemented a custom file systems format that I call RAM disk. So yeah, this is how it works. And let me show you what it looks like in code. So VFS. So this is what so this is what a file system, any file system should do for my operating system virtual file system to use it. It should have a create, remove, read, write directory, write directory, remove directory entry, and some function, populate VFS. So if you implement this, you will be able to use that file system in this VFS. And then in this VFS, we have a node which has a few things like the node type, the file system, the resource is just the inode, the size, and device ID, because inode can be same but device ID will be different. Then some children, parents. So this is a graph node, and then I have a actual VFS which does all the things like make directory, make file, and this does that by calling the underlying file system. So it does like traversing, and then in the end it has to call the file system's make directory or create. If I go to its definitions, so I have created a RAM disk file system. So what RAM disk file system is, it is a file system that is not using actual IO device like SSD or HDD, whatever it is called. It is just using a imaginary file system on RAM, and its format looks like this. It has a super block, inodes, data bit set, data block. So again, more theory to read, but this has some meta information. This has information about which inodes are present, which data blocks they point to. Data bit set is a bit set to specify which data blocks are free and data blocks. So yeah, this is just again not a very good implementation, but it works. And I use this, so I initialize this at the boot time. Here, as you can see, create a RAM disk with device ID 1. I create some directories called proc and dev, and then in the k thread, by the way. Okay, come on. Okay, where is that? Okay, so in the k thread.cpp, every time a kernel thread is created, it also creates a standard input and standard output file here. And whenever it wants to read input or write data, it writes to its standard input and output. So it is similar to file descriptors, right? I've created a file descriptor as well, which is just a file and its read and write offset. So yeah, that's how file system works. And now, because it is so good, let me show you a very cool trick I do. Or I mean, it's not that cool to anyone who knows how this stuff works. So the way I do rendering, right? Now let's talk about rendering, because it is related to this. So because for Snake Game I need to do rendering. The way rendering happens is through a memory map device, and how that works is this. So there's some memory address, right? So there's some part of the RAM, some continuous part of the RAM. Actually, if I'm showing continuous part of the RAM, let me show you this. So this part of the RAM maps to the 2D representation of the screen with all the pixels. So it is in the row major format. So 2D arrays are also stored in linear fashion, right? So if you have a array like this, yeah, I'm so bad at this. 1, 2, 3, 6. Then your multi-dimensional array would be stored like this: 1, 2, 3, 4, 5, 6. This is called row major. So this is a row major representation of device pixels, and if I set this memory in RAM, the pixel in the device will update to show that color. So what I did is I created, now this might not be a very good idea, but I wanted to provide a simple interface for graphics. So what I did is in the kernel.cpp, I create a file called dev/fb frame buffer, and I use a file system called frame buffer file system. What it does is, let me go to frame buffer.cpp. There's nothing to create or remove, or create directory, remove directory, these things. The only thing it supports is read and write, and it will essentially act like a proxy to this memory address. So whenever you want to do some rendering, you can just write to this file. So my graphics object does exactly that. When I want to put a pixel, I get the offset for that position, and then I just write that color value using my VFS. So that's how clear screen and fill rect is. Now, if you have some experience in game development, you would know that this is a very bad idea. What I should do is, on all these calls, I should write to a secondary buffer, and then in the end call a render command or something like that, that would swap the buffers and render everything at once. That would be very quick, and also that would remove the flickering. So I know how to remove the flickering, but I have not removed it. And so let's talk about why that is the case. So this implementation of operating system sucks. I mean, it's so bad that if I change the build flag from debug to release, it will stop working properly. It probably goes into some undefined behavior somewhere, and it will stop working. Now, obviously, I did not want to write a very robust code and everything, because that's not how you write your first operating system. At least that's what I think. And so I cut corners at a lot of places, and eventually I got into a state where the more code I write, the much more I have to debug. So much more that it's just better at this point to rewrite this entire operating system and then add new features. And that's exactly what I've decided. And also, the reason why I cannot add double buffering is because I would need to allocate more than 512 pages to allocate enough memory to create a separate buffer for that. But my memory manager gives up on that. It just fails, and I'm not able to debug it either. So I would have to rewrite the memory manager at least anyways. So yeah, a lot of things are falling apart, but I created a Snake demo just to make the video more interesting. So yeah, that is the situation. This is a implementation of an operating system in kernel space only. It is not that bad. It's not that good, right? There's a lot of corners cut, lot of undefined behavior, lot of errors that go unnoticed, and that is why I cannot build upon it, and that's why I've decided to rewrite. That's essentially the future of this operating system, which I'll probably do a bit later. All right. So yeah, that is the future. Another thing I would like to mention is I've actually started doing some work to make sure the future is secure. So you might have noticed that I require a lot of things like allocator, bit set, concepts, string, vector, right? These implementation are also very bad. So what I did is I created a new project called Core X, which would be a CPP header only library, which is actually, that contains all these utilities and more. And it is written in such a way that there are only few places where there is assert, and every other place the error is returned. Because one more thing that I forgot to mention is that in C++, for exceptions to run, we need environment support, and for that there will be a lot more work needed, and exception sucks in general, right? So that is why in this library I have created this Rust type object that returns an error and a result. So this way, and all these things are minimally tested as well with unit tests. So that's the future. I'm gonna stop working on this, and this is as far as this version of demo as goes. A pretty good demo for in kernel space for what I've done, I guess. That was it. I guess I have covered everything, how I've done them, a slight overview, and I hope now you have an idea and steps and resources to know how to do OS dev on your own. So yeah, hope you liked this video. If you did, leave a like, subscribe, and I'll see you never. I'm kidding. Next time. Because even after months, I came back.